Yeah, perfect. Yeah, hello, ladies and gentlemen. Welcome to the talk, How to Build the Most Efficient Concept Car in the World at the Big Tech Day hosted by TNG. This talk is also streamed, so if there are any questions in our Slack channel, or if there are any questions in the stream, please use our Slack channel. And now I'm very delighted to introduce you the key players within the TUfast Eco Team from the Technical University of Munich. This determined team of students has taken on the global challenge of creating the most energy efficient concept car in existing. Among these teams of 80 people, so that's quite a large team, we have here Yannis Bays, Pedro Redondo, and Gleb Lialin. Yannis serves as the aerodynamic lead within the team. His focus and ingenuity have led to a remarkable 11% reduction in air drag. Sharing his powerful skills, Pedro brings his flair for the mechanical engineering to the role of the head of running gear. Before he was a steering system lead. And lastly, the team is under the lead of Gleb, the team manager for the TUfast Eco Team, combining his education in management and technology with his leadership skills. He managed to acquire some sponsors and, of course, manage this whole team. He's currently preparing his semester in Singapore. Please join me in welcoming this team, and we are looking forward to your talk. The stage is yours.
No, you hang up. Okay, thank you. Thank you also to all of you for coming here and taking interest in our project. To give you also a short introduction about the team itself. Like introduced, my name is Gleb. I'm the team manager of the team. The TUfast Eco Team is a student team of over 80 students at the TU Munich who builds highly efficient and autonomous concept vehicles. We're not doing this for the first year. We actually started out in 2009 when a bunch of us, just really 5-6 students at TU Munich, built the first small prototype vehicle. By then it was a completely different form, was way smaller. And then year by year, iteration by iteration, the cars got more sophisticated, more interesting, and also more efficient. So really following this philosophy of like creating something new, looking at the car that was done the year before, making it better, then be happy with the result, and repeat again with the next generation. The question might come up, why do we do this? Because obviously the car that we are building, I don't know, maybe some of you already saw it, it is like up to the entrance to the platform. If not, I highly encourage you, like right below the food platform, our car is actually today here, and you can look at it. So again, why do we do this project? Because the car will never drive on the street. We are not selling it. It has not really monetary value. It has, in the end, two purposes. The first one is we are going to competition each year. Every year there's an efficiency competition hosted by Shell. Across Europe, this year we were in France, where over 100 teams from across the world come together, all from universities, and compete in the efficiency of their car. It works the way where you drive multiple laps, you have to stop every lap, you have a time limit, so you cannot go too slow, and it is measured how much energy you consume. The team who consumed the least energy wins the competition. We in this season got to the second place, so we didn't manage to build actually the most efficient concept car in the world, but this will still come. The second purpose of the whole project is that we believe the cars that are currently out on the street are way too power hungry. In a world where the scarcity of energy is one of the great challenges of our time, it is of utmost importance that we find ways to substantially reduce our energy demand per capita. And individual mobility is one of the points where we can address it. It is one of the core contributors to our energy demand. So we are trying to really reduce the power consumption of the vehicle of the city of tomorrow. If you want to build a super efficient vehicle, there are multiple variables you have to address. Most important ones are, for first, the weight. The heavier the car is, the more force it takes to accelerate to the desired speed. Second of all, aerodynamics. I guess aerodynamic drag is the force exerted in the car as it moves through the air. It is very important to really decrease the aerodynamic drag coefficient, especially at high speeds. Lastly, there are a lot of other losses throughout the system. If you go from the motor to the wheels at each component, at each system, you really have to try to optimize every point and minimize all the losses, be it mechanical friction, some electrical losses. Overall, we then started out from more or less from scratch. We had no budget at the beginning of the season, we had no real team, and we had no design idea. What we had was some of us, including the 3 standing here today, we were there already in the season before. So we had experience as members and took then on more responsible positions. But that was really all we needed to give us a really good start in recruiting new team members in the lecture halls and distributing responsibilities out along. The following months then were used to design and develop our car to become what you can see now today. Already during design phase, we had started out our production. This meant that from morning till night in 4-hour shifts, you could find 2 to 6 of our team members in the workshops in Garching, working on the car, be it sanding, be it chemical application of molds, laminating the car. And they did this all next to their obligations in private life in university. So none of us get paid. We all do this out of motivation. Obviously, this makes cost of labor very low, but the question of motivation becomes way harder because you have to get some intrinsic motivation that has to be there. What we can definitely say is one of our greatest assets was our diversity. Across this 80 people, we have 34 different nationalities. And was it there at least, like the points? Mm-hmm. Okay. No? Okay. Then really this diversity provides a very unique dynamic where like everyone feels very welcome and doesn't fear to put in really radical ideas. And every one of us can say that after this season, because we are now actually almost at the end, everyone is very happy to be a part of it. And the experience you take home and lessons you learn for your life is something you will never forget. We not only become better engineers, better managers, better team workers during it, it has a very lasting impression on the way we do our work. If we like stay in the context of cars, if we look at one and design one, we're not trying to go like for the high speed, big acceleration or maximum comfort. We go for sleek design, efficiency, and try to get the same output with a fraction of energy cost. And today we're here to, first of all, tell you how exactly we did this, and also maybe to connect this to TNG. As we said, the car doesn't have monetary value. We don't sell it, but still we have quite some expenses that we need to cover. So we're not only here to engage with you and tell you what we did about it, but also to maybe show TNG that what we did with the sponsoring we got and that the money was well invested. So now we will hand over to Pedro as our head of running gear and Yannis as our aerodynamics lead. We'll give you a deep dive into how we managed to really optimize to the absolute optimum our lightweight design and the aerodynamic drag.
Hello. First of all, as an engineer, I would also first apologize for not having the same public skills as our team manager, public speaking skills. So I brought my cards. But, well, thank you for joining us today, well, as we dive into the fascinating world of automotive design. My name is Pedro, and I'm honored to be here as one of the presenters in the Big Techday, as we discuss how we design and build MOOC 23. While Gleb introduced our project and the exceptional team behind it, and Yannis will share insights into the aerodynamic optimization of the car, I will now take you on a journey through some of the methods of lightweight design that our team have used to make this engineering marvel possible. Using simulation techniques such as multi-body simulation, topology optimization, finite element analysis, and one of the advanced projectors behind it called selective laser sintering. Sorry. There you go. But before we dive into all that, why even is weight that important? Aren't cars nowadays actually getting heavier? The truth is that weight plays a critical role in a car's performance. And the increasing weight of the cars has indeed been a concern. This trend is mostly due to the growing popularities of bigger and bigger vehicles, such as SUVs and trucks, as well as the prioritization of safety, leading to the use of heavy materials, as well, and heavy modern creature comforts, such as powered steering or heated seats. We, however, have recognized the significance of reversing this trend and focusing on lightweight design, while still aiming for, of course, for a safe and reliable car. So we had to go back to the drawing board. By shedding unnecessary mass, the car will accelerate and brake faster, handle better, and steer more reliably, thus producing a safer car to drive. Heavier cars also, of course, require more energy and resulting in greater emissions. That's why our car weighs less than 4% of a modern SUV and is thus 50 times more energy efficient than a normal road car. It does not, however, have Apple CarPlay yet, but we're working on it. It goes without saying that the car is a prototype vehicle that was made solely for competition use. It's far from being road legal, and let's be honest, who doesn't like heated seats? But the goal of our project is beyond that. It's to lead the way into the future of automobility with top-of-the-industry design methods and reach efficiency ratings that are unimaginable for consumer vehicles. So that one day, some of these technology at least, will be used in consumer products or, worst case, Formula One. Reaching such a system that works together with the maximum efficiency and minimum energy losses is, of course, no easy task. In scenarios like ours, where we're literally counting grams, understanding how to spend this weight is an extremely important task. The material choice, for example, is, of course, one that goes through multiple revisions, and until we have triple-checked every single simulation with a big enough safety factor for manufacturing defects or small damages, the decision cannot be made. The design of such complex parts, of course, also plays an important role. Having iterations and iterations of our parts in the last few years in all different generations of cars, you can see them shrinking every year. Starting in 2017, when we first competed in the urban concept category, reaching now, in our opinion, very close to the minimum weight possible. But you can't just shave away material from anywhere. You need a thorough understanding of the distribution of forces and the minimum amount of material in the walls to create a part that will hold. In our case, a program optimizes the shape by slightly changing the design according to the parameters, checking back on the simulation to see if the part will still hold, and then improving it again, closing a loop. To start off this long journey that was designing and building a car, let me go through the process of the extensive simulation that went into each and every component. The first step was to optimize the drive of a competition track, to design the suspension dampers accordingly, and then this allowed us to calculate the forces on the car and define the suspension kinematics, which led us to the first big hurdle of the process. Yeah, this is just the beginning. To analyze how the forces distribute themselves in the complex arrangements of carbon rods and metal mounts, we use a process called multi-body simulation. Multi-body simulation is a computer-based technique used to study how different parts of the system move and interact with each other, which is just a complicated way of saying that there are a bunch of mathematical equations and simulations that are used to understand how the parts interact with each other and how the forces spread throughout the system. It's like testing how the car will work before even actually building it. The simulation gave us a good understanding of where the acting forces concentrate, and it prepared the ground for what was to come. And there was still a lot to come. By knowing how the forces interact with each other, we could then restrict the parameters and use a process called topology optimization to design our parts. Topology optimization is a powerful computational technique used in the design process to determine the distribution of material within a given design space. It involves analyzing the structural performance and loading conditions to identify the most efficient shape of a part. We first set the design goals and the constraints using the acting forces that we just calculated, and then the algorithm explores countless design possibilities for tens of hours at a time just to find the optimal configuration. Here you can see 3 different generations of the same part, beginning with a milled version and then getting slowly into the final optimized part. So if you feel like this speech is going a little too long, try waiting 30 hours in front of the computer for the simulation to finish. Throughout this process, we were able to uncover innovative and unconventional geometries that maximize strength and minimize weight. By removing material from non-critical areas and redistributing it to areas with higher loads, we achieved a highly efficient design that maintains structural integrity while significantly reducing weight. Topology optimization has been instrumental in pushing the limits of design, allowing us to create lightweight components that were previously unimaginable, ultimately contributing to development of the most efficient car in the world. This iterative design process incorporates finite element analysis to provide with recursive feedback on the simulation, removing material little by little and re-evaluating the stress zones of the parts until we reached our final design. Finite element analysis, or FEA, is a computational tool used to evaluate and ensure the structural integrity and performance of each component. It's widely employed in the field of lightweight design, of course, to optimize the strength-to-weight ratio and ensure the components can withstand various forces. FEA works by dividing the complex geometries into very small elements, and then each element is simulated and its behavior is analyzed under different loads, testing it to see how it withstands forces such as vibrations or bending and pressure. By simulating the interactions between these elements, FEA can predict how the component will respond to various stress scenarios in the absolute worst driving conditions, like a full brake while doing a tight curve from top speed, which obviously we don't want to do, but if a competitor just parks a car in the middle of the track, which has happened before, we might have to. In our project, FEA played a vital role in the design process. We utilized FEA to analyze almost all components of the car, in the suspension, but also in the chassis and body parts, as Yannis will go into. And it also enabled us to identify the general potential areas of high stress, deformation, or failure within the design. This information allowed us to make the informed design modifications that I mentioned and optimize the components' shape, material distribution, and structural reinforcements. The analysis results from FEA can inform subsequent design iterations, allowing us to further refine and improve the lightweight components either by hand, removing material where we see it's not necessary, or by closing the simulation loop, as I mentioned. This iterative design approach ensures continuous improvement and helps us achieve a design that maximizes performance and reliability. Of course, these complex geometries can't just be carved away with the CNC machine. Trust me, we tried, but nobody wants to just get a huge block of aluminum and carve away this complex structure. To produce almost all of our metal mounts, we count on a state-of-the-art manufacturing process called selective laser sintering, or just 3D sintering for short. This is an additive manufacturing process that consists on heating powdered metal and fusing it together layer by layer with a laser that creates a three-dimensional object. This allows for much more design flexibility, as virtually any shape can be reached. Of course, within the design and production methods, already there is a lot of choice and a lot of different methods, but there's also thorough consideration into the materials that will be used. With titanium, we could produce parts with very thin walls while maintaining incredible stiffness. With high-strength aluminum alloys, we were able to produce lightweight and different sized parts with the needed stiffness according to the alloy. For the rods, we chose to use carbon fiber, as it just has an incomparable strength-to-weight ratio, especially with high axial strength. Putting all these methods together, we were able to design our metal mods, and most excitingly, our uprights. These parts that weigh only 210 grams each sit at the very center of the wheelbase assembly and transfer the entire weight of the car into the wheels. Our goal is to achieve a geometry that perfectly shows the flow of distribution of forces in a seemingly organic manner, thus producing a part that is incredibly lightweight while still being very durable. With a better understanding of the acting forces on the car, as well as an optimized simulation loop, we were able to achieve these amazing results. With a combined weight ratio of around 50% of all of our metal parts in comparison to MOOC 22's already optimized lightweight design, we were able to reach such amazing results. With the use of such design techniques, we achieved a total weight reduction of more than 7 kilograms just on the running gear system, reaching an astonishing 17-kilogram running gear system that can make the car move and stop, most importantly. With all these advances, we created a lightweight and robust car, helping us achieve our goal. In conclusion, by prioritizing efficiency and utilizing cutting-edge materials and technologies, we were able to be leading the charge into the future of mobility. But now, I'm going to invite to the stage Yannis to continue explaining the development of the car.
Greetings, ladies and gentlemen. I extend my warmest welcome to all of you, and I'm honored to be here today as the aerodynamics lead of MOOC 23. I am Yannis, and it is my privilege to follow the exceptional introduction made by Gleb and the presentation of lightweight design aspects by Pedro. Firstly, I would like to take this opportunity to shed some light on our vehicle body aspects, continuing Pedro's philosophy regarding the lightweight design. Although our main concern is the optimization of the passenger cell, as it provides structural integrity, enhances performance and handling, but also ensures safety for the occupant, the appendage parts that shape our vehicle body are also important. Then, as a direct connection to the vehicle body, we will dive deep into the aerodynamic aspects of MOOC 23. My role in the team was to ensure that MOOC 23 glides through the air with unparalleled efficiency. I'm going to share all the intricacies of MOOC 23's aerodynamics, the insights and innovations that make it truly great, starting from the concept of our vehicle, continuing with the optimization methods, and then the methods used for a fully automated design loop. All in all, the workflow that ensured that our car is aerodynamically exceptional. Yes, one of the two main components of the resistive force acting on a vehicle is the rolling resistance force. Rolling resistance coefficient times the mass of the vehicle times gravitational acceleration. And this is true at least for a vehicle on a level surface. Of course, weight plays a massive role into the efficiency and the energy consumption. Therefore, one goal was to build a car that could weigh lighter than its driver. This season, our focus was to reduce the weight of our passenger cell, the monocoque, even more. The unibody solution to have this main structure while carrying all forces when driving still makes the best construction method, especially for prototype cars like ours. Now, to quickly understand how stability of carbon fiber parts works, multiple layers of carbon fiber sheets are stacked above each other to be then connected to the resin. This creates a very stiff structure against bending. To increase this, core materials such as aluminum core, shaped like honeycomb, is added in between to create a sandwich structure. The theory is to bring distance between those carbon layers, and by this we increase the bending stiffness even more. Still, with the same safety and load cases as our previous car, we were able to reduce the weight of the passenger cell from 18.6 kilograms to only 14.7 kilograms, a weight reduction of a striking 21%. But the monocoque is only a part of our vehicle body. We kept on continuing to minimize the weight of our entire vehicle for the ultimate efficiency. This was done through inspecting various carbon fiber and other material types, simulation, and of course experience gained from the years before. In the end, we were able to reduce our weight of the total chassis by 19%, from 31 kilograms to 25.2, carrying all loads, protecting the drivetrain and electronics, and forming the aerodynamic shape, which will be our next topic. Aerodynamic drag, or simply drag force, or even simply drag, is the other important term in the resistive force acting on a vehicle. Aerodynamics remained quite in the background for many years, as the majority of the car manufacturers' efforts for reducing fuel consumption were focused on engine improvements. Reducing aerodynamic drag on a vehicle can also help reduce its energy consumption, therefore its carbon emissions, making it an important consideration for reducing our carbon footprint. Aerodynamic drag is the force exerted on a vehicle as it moves through the air. Probably many of you are familiar from high school with its associated formula. It is caused by the resistance of the air to the vehicle's motion, and it's proportional to a parameter that represents the shape of the vehicle and to the square of the velocity. The faster a vehicle moves, the greater the aerodynamic drag it experiences, and the energy required to overcome the aerodynamic drag increases exponentially. Why is aerodynamics important in such a car with such low speeds? This is probably one of the most, if not the most frequent question I've been hearing when aerodynamics of this car is being discussed. And to be perfectly honest with you, this seems very reasonable at first. I just mentioned that the drag is proportional to the square of the vehicle speed, so what's going on here? There is one thing missing from the story, and that's the weight of the vehicle. It is something that has not been intentionally mentioned yet. Indeed, in a passenger vehicle of 1.5 tons or even 1 ton, at low speeds the aerodynamic drag is not as important. On the other hand, MOOC 23 has a curb weight of only 65 kilograms, proving the lighter than its driver phrase we saw before. With such a weight, aerodynamic drag becomes important even at average speeds of 25 kilometers per hour. How important? Real track data shows that the energy required to overcome the aerodynamic resistance is around 35 to 40%, making up a significant amount of the total energy. But what about the shape of our car? How do we design a vehicle that gives the least aerodynamic drag when we talk about the same velocity? Oh man. Yeah, got it. From what has already been discussed, it becomes very clear that we need a systematic way to assess our vehicle shape. This can be done in terms of computational fluid dynamics, CFD in short, or wind tunnel testing. Wind tunnel is supposed to be more accurate as you conduct an experiment with a real vehicle under real-world conditions. However, the associated costs are high. Also, you need a finished vehicle, otherwise what are you going to test? One possibility is to use a scale model, but this model should be versatile and adjustable, so one must always be able to adjust it so that it represents the geometrical changes that you do, which cost time and money. In CFD simulations, we do practically the same thing, but virtually. We place our car in our virtual car in our virtual wind tunnel. In this picture, you can barely see the car, and trust me, the scale of this picture is not wrong. The dimensions of the wind tunnel real or virtual, must be significantly larger than the vehicle in order to obtain correct or accurate data. The larger the wind tunnel, the more safe we are, so to say, but this comes with an increased computational cost. This is a significant aspect of our simulations, as we must find the perfect balance. CFD simulations provide detailed information about how the air enhances our car, allowing us to evaluate and modify the car shape to reduce drag. The simulation of different design configurations can be done relatively quick in order to evaluate their performance and identify areas of high drag. Since the simulations are much faster and less expensive than wind tunnel testing, they allow us to reduce the overall time and cost of the design cycle. Our previous car, Moog 22, showed also strong aerodynamic performance. Therefore, the development started with one phrase in our minds: evolution and not revolution. Among other areas, we decided to focus on two main areas where we assumed that we would have a large reduction in aerodynamic drag. Firstly, covering the front wheel arches was our priority, because as the car moves forward, air flows around it, and some of that gets trapped inside the arches, and then the aerodynamic drag is increased. Using wheel spats, as they are called, the airflow interferes less with the rotating wheels, reducing the drag. It seems easy, right? Just an extra surface that covers the wheels. Unfortunately, no. Although it is a relatively easy implementation, we put a lot of difficulties to the running gear team, and Pedro must hate me for that, as the guys there had to reduce the wheel track of the wheels to the absolute minimum, so the wheels could steer without touching our new component. Another modification is the change in the shape of the tailgate, as it defines the airflow in the critical wake area, the area behind the vehicle. It is the area where the largest amount of aerodynamic drag is generated. For this reason, we introduced a dent in the middle of the width of the tailgate. And I must admit, we are very proud of this dent that you see here, not only because it has an aerodynamic benefit, but because it is a result of using an optimization technique called adjoint surface optimization. Adjoint optimization is a numerical method used to efficiently solve optimization problems by calculating the sensitivity of an objective function, a mathematical function that gives us an idea of which local area has which impact on the cost function. In our case, things are quite simple. The objective function is the drag force that must be minimized. That means that the algorithm calculates backward from the objective function to see how its node or its little part of the vehicle affects the objective function. Based on these results, we can calculate or construct the sensitivity map, which shows where should the geometry be changed to fulfill the objective function. Finally, the loop closes by transferring this information to the morpher, which updates a numerical mesh indicating our updated geometry. And this is exactly what you see here in the GIF. Here, you see 10 iterations or 10 full loops of this method. I don't know what about you, but to my eyes it seems spectacular. Indeed, it's a very sophisticated and powerful tool, but the engineer's input is still important and essential. Such a loop comprises of computationally very expensive chain of operations that could last days. And in the meantime, you can do nothing but practice your patience skills. And because this method is more efficient and more numerically stable when applied to relatively small areas, the choice of the area is also crucial. With all these modifications in the outer shape of the vehicle, we managed to reduce our drag coefficient from 0.16 to 0.13, a reduction of around 17%, a huge achievement. The car has a drag coefficient of 0.13, and in order to comprehend better this number, I want to inform you that a modern production car has a drag coefficient of around 0.25 to 0.3, depending, of course, on the segment of the vehicle and the effort put on aerodynamics. Lastly, we would like to talk about some optimization techniques. Not only the actual simulation, but even the setup of the simulation can be time-consuming, as a plethora of parameters must be defined one by one. But when a significant for the numerical simulation geometrical changes occur, the exact same simulation parameters can be used without any further implications. This was the motivation that led us to the creation of template file and simulation macros. A template file is a simulation file that contains everything but the vehicle model. The dimensions of the wind tunnel, for example, are defined in this file. We can have a new vehicle configuration, but we can use the exact same virtual wind tunnel. Simulation macro is a script that stores every single setting required for setting up the whole simulation. Parameters such as the velocity of the wind and its direction, and also whether we want to include rotating wheels, are defined there. We need to prepare both of these files manually only once. In between the two steps, the geometry must be imported by the user. By using this workflow procedure, the pre-processing of our simulation can be reduced from around 45 to only 3 minutes. This approach is also followed for post-processing of the simulation, which is probably the most critical part of the design loop. Overall, pre- and post-processing chain results in substantial time gains, giving us, the designers, more time for what is needed. Understanding the flow phenomenon, proposing changes, and finally, generating new geometries for simulation. Now, I'm handing back to Gleb. Yeah.
All right. So after Pedro and Janis gave us some really great insights into lightweight and aero, we want to shed a little bit of light on, for us, the final variable that is important to complete the vision of a futuristic vehicle. We think cars should not only be very efficient, but they should also drive autonomously to make driving accessible and effortless for everyone. Autonomous driving not only gives you the possibility to have a safer driving on the streets, but also to make the car more efficient, because if we can make the cars on the traffic lights, on intersections, start and stop synchronized, then we can significantly reduce the energy that is needed for these acceleration and braking periods. So for that, our autonomous team put in a lot of effort to create a very sophisticated system that starts with having 1 LiDAR and 5 cameras on the roof. I don't think you see it in this scheme, but you can look at it outside, which gives us 360 vision, independent whether the car is going at high speeds at different angles. It always sees everything around it. Additionally, we have in the front 1 depth camera, which sees 1 million color point per second and can detect 3D objects very well. And a long-range LiDAR, additionally to the LiDAR on top. The long-range LiDAR has a range of about 300 meters and can thus plan way better in advance and create a better plan, even if you go quicker and covering meters at a higher pace. Then in the back, we have 1 GNSS sensor, which can locate the car at sub-centimeter precision all around the world. And our computing unit, which is actually half the weight, so we're also saving weight on the autonomous system, and still double the power than last year's computer. And the computer has next to it a real-time machine, which then actually is doing the navigation. It's converting the motor signals to make the motor turn as the machine, the computing unit calculated. All the data that all the cameras collected is combined in the video grabber card, which then transfers it to the computer for computation. So yeah, exactly this. And there you see the video grabber card as far as I know. Come on. Yeah, exactly. Our steering is also then done autonomously. In comparison to the manual steering, we have then a steering motor that is directly attached to the column of the steering system, and a powerful motor controller which can even at high forces steer very precisely and directly. Lastly, all these fancy hardware thingies don't give you too much if you don't have at least some kind of functional software. That's why we have a self-programmed neural network that is trained on thousands of hand-picked data to recognize the real world, create a map, and then plan an autonomous trajectory that it can follow. So overall, we went really above and beyond to create an autonomous vehicle that comprises lightweight design, aerodynamic optimization, and minimal losses across all systems. Our goal of this car is to show what we think individual mobility should be about. We wanted it really to be an inspiration and a vision for what should follow in the automotive industry. Now we will look at one final video where the car is kind of revealed. Here you have a picture from the competition. I think that's also nice. Also for the ones who didn't see the car yet, this is the car that is standing down there. You can have a look later. So now to the video, right? Perfect. Then, thanks for listening, and we're now very open for discussion with you, for questions, if you want, critique. So feel free.
Yeah, thank you for the amazing insights and that great challenge. Are there questions in this room?
Hi, thank you for the wonderful presentation. I just had one question because I used to participate in also motorsport. How constrained are you by the competition's rules? Because in some motorsport for students, you have like thick books that you have to learn. And I was wondering how much would it change if you didn't have those guidelines?
Well, we definitely have a set of rules that we have to follow, maximum size, minimum size, all the dimensions. We are basically in the maximum of everything that as it goes to, for example, the length. The car is as long as it has to go, as can go, to minimize the drag. But other than that, we have little limitation to the actual outside shape of the vehicle, and the motor size, motor type, everything is very, very loose. So we are very free to optimize and experiment with different types. We actually have a very, very optimized system, and we are very proud of the entire suspension through the drivetrain and the vehicle body in general. And if you compare to different teams, they have completely different designs that aren't not like a Formula One car where you, from the outside, you can basically not really tell them apart.
I can also. Yeah. I can. Microphone? Is it on? Test. Okay, the microphone doesn't work. Now? Yeah, I can. Yeah. I can also answer to that question. For example, if the regulations allowed us, the car would be even longer. This is my dream, basically, because I can. Yeah, because. We can convert the upper and the lower side of the vehicle to have even less aerodynamic drag, but also, moving the car even lower to the ground. There's also restriction in the ground clearance. Yeah, these are, you can imagine these two different designs that could be on the car.
I think there was another question over there.
Hi, it's working. Yeah. Thanks for the presentation. Maybe you mentioned it and I just missed it. How like where does the car draw energy from? Like which type of fuel? Is it like an electric battery? How?
Yeah, of course.
And also, as a like a follow-up to this, what is the current autonomy of the car?
Yeah, the car has, of course, a battery. It's a battery electric vehicle. There's no restriction in the battery because this is not the target of the competition. You could have like a very big battery, but it doesn't really matter. The final target is that you must be able to complete the scenario for the competition, which is you have to complete in a certain amount of time, a certain amount of laps, and using the least energy. So if you fulfill that, then you're good to go.
I can also add that we don't have a theoretical maximum because we can exchange the battery and make it, since it's not a production vehicle where the battery is embedded in the vehicle, we can make a battery bigger or smaller. And little spoiler alert, but we are attempting this year the longest electrical drive of a car in one charge. So we obviously build a much bigger battery pack and put it in the back of the vehicle, and we are attempting it again in the end of the year. Thank you.
Okay, then I have a question from a remote participant to Pedro. The models of the mechanical components you have shown are all continuous solids. Do you allow for different types of geometries in your topology optimization to increase the structural strength of to material amount ratio, like honeycomb structures?
Yes, for sure. So in the particular examples that I showed, I was mostly talking about metal parts. So the parts that we have, the geometries that we have, are going into. Oh, sorry about that. Are compared locally. Maybe I should stand where the camera is facing. So yeah, this is all in comparison to the metal parts. But for parts where we actually see a benefit to using carbon fiber and different alloys and a lot of different possibilities, we do simulate completely different scenarios. So for example, our monocoque is made of a sandwich structure using aluminum honeycomb. So it composes of, as Yannis better explained, some layers of carbon fiber followed by aluminum honeycomb and sandwiched together another layer of hard carbon fiber. Additionally to that, we actually have another simulation optimization that we have for the carbon fiber layers and how to position them and how to better optimize the weight so that we don't have one full global layer, as we call it, but actually we have only carbon fiber where we need it. So we have the global layers and then we have reinforcements, especially where the material is needed. So yes, we do also make this analysis. Hope it answered the question.
Then I would like to come up with a question. You mentioned that your simulations take up to 30 hours. What infrastructure do you use? Because it seems like adding more power, computational power, could be sufficient or could help.
Of course, yes. We have multiple different techniques. We have a few for smaller tasks. We use just powerful computers. We also make use of the university's cluster. So we have access to a cluster of computers, which make the computation time much faster. But still, it's a very, very time-consuming task.
I can also answer to that question because of the CFD simulations. They take also a lot of time. Also, this optimization thing that you saw, it's basically 10 standard simulations, so to say. And each simulation takes about, depending on the number of cores and nodes that you are using, let's say about 7 to 8 hours. That includes the meshing and the actual simulation. But of course, we are talking about a quite large model for that simple car, at least in terms of the outer shape. So yeah, we are very lucky to be part of the Technical University of Munich because we have access to such good infrastructure that we can use to optimize and further optimize our models.
It could take way longer if you have less
Yeah, of course. We're talking about hundreds of cores.
Yeah. Okay, looking at the clock, I would say if there are way more questions, other speakers are available for a question afterwards, especially now during the lunch. There said we have 4 lunch areas, so here Rotunde, then Highline, Motorboat, in Beer and Garden, and the Kessler House. So there I would say enjoy your meal, and thanks again to the speakers for the great talk.
Thank you.